Hello everyone. In the continuation of our lecture series, today we are going to discuss some important point related to hash diagram. In the last session, we talked about hash diagram, that what exactly a hash diagram is, how one can draw a hash diagram for a given poset. Today we are going to discuss some important terminology related to the hash diagram. The first thing is what we are having comparable and non-comparable element. Okay, so in today's session, we will try to understand that what we mean by a comparable and non-comparable element. Then we will try to understand upper bounds, lower bounds, maximal element, least element, greatest element, supremum, infimum, which play a crucial role to decide whether a given poset is a lattice or not. Okay, so let me share the screen. So firstly, let us try to understand what we mean by comparable and non-comparable element, because the rest of the part is based on these things. So comparable element, two elements of a poset are called comparable if they are related to each other. That means we can find A or B. Comparable means what? We are able to decide which one should be on the lower side of lower side in hash diagram, which is smaller, which is larger, not exactly in terms of magnitude, but in terms of the relation. So two elements are said to be comparable if they are related to each other. Related to each other means what? If either A comma B belongs to R or B comma A belongs to R. A is related to B, which is having the same sense that A comma B belongs to R or B comma A belongs to R. This we use when we are in the process of finding supremum infimum, which is the least element, which is the greatest element. The first thing is what from the elements where you want to get least or greatest, they must be the comparable. So if A comma B belongs to R or B comma A belongs to R, the pair of elements are called comparable. On the other side, if ne if neither A comma B belongs to R nor B comma A belongs to R, then that pair of elements called as non-comparable. Neither A comma B is in R or nor B comma A is in R, called as a comparable element, non-comparable. For example, if I am having a relation which is having element 1 comma 2 and 1 comma 3. Okay, so now I need to decide that out of 2 and 3, which is least one, which is greatest one, can I decide it? The answer is no. Why no? Because 2 and 3 are non-comparable. We can't do the comparison between them because 2 comma 3 is not there in your R and 3 comma 2 is also not there in your R. If a pair of element is missing from your relation R, we call them as non-comparable element. In the same side, after comparable, non-comparable, we are having one another point which is called as lower or upper bound or successor or preceder. Successor or predecessor. Okay, successor or predecessor. Now, when I'm saying A comma B belongs to R, when I'm saying A comma B belongs to R, then this is called as a lower bound of B. And this is called as the upper bound of A, upper bound of A. So when a pair of elements are comparable, then the input, The element which is the first one is called as the lower bound of the second one, and second one is called as the upper bound of the first one. B is called as the successor of A. A is called as the preceder of B. So this is how we can understand what we mean by upper bound or lower bound of an element. So if they are related to each other, then the first one is called as the lower bound and the second one is called the upper bound. Lower bound of the second element B, upper bound of the first element A. This will be useful, or this can be directly taken from the Hasse diagram also. So suppose that a Hasse diagram is there which is having these three elements. This is let it some Hasse diagram. So A is the lower bound of C. B is the lower bound of C. So C is having two lower bounds. A is C is the upper bound of A and C is the upper bound of B also. Now out of A and B, which is lower bound or upper bound? We can't decide because they are non-comparable. A comma B is non-comparable. I can't reach from A to B without changing the direction. If I am taking this path, I am moving upside. I can't come on lower side. So this is how we can say they are non-comparable elements. Or out of A and B, we can't decide which is upper bound and which is lower bound. In the same manner, as a result, every element is upper bound as well as lower bound itself. Every element is upper bound as well as lower bound of itself. Let us see what exactly is written. Let me rub these things. Since the relation is reflexive, we are talking about the posset. We are talking about the posset, and posset is always reflexive, anti-symmetric, and transitive. Okay, so every element is lower bound as well as upper bound of itself. Lower bound as well as upper bound of itself, because A comma A is always the part of R. Hence, we can say A is a lower bound of A itself. Like, since the relation is reflexive, so A comma A will belongs to R. So A is the lower bound of A is the upper bound of A. So we can say every element is the lower bound as well as upper bound of itself. Another important point is what? The lower bound and upper bound of an element is not necessarily unique. It may more than in number. Like one example I have taken, which is A, B, C. So in this diagram, B is having two lower bound. B is having two lower bound. So lower bound and upper bound may be more in number, maybe more in number 1, 2, 3, or any. Now, talking on these bases, let us talk about some more terminology, which is the first one we are having is maximal element. So an element of a poset is called as a maximal element if there's no other element, if there is no other element which is the upper bound of this element. Now, A is called as a maximal element if there does not exist any other B. No other B is there which is upper bound of A. Now it means what? A related to B means what? A comma B belongs to R. That means B is the upper bound of A. B is the upper bound of A. So what definition is saying? We call A is the maximal element if there is no element which is upper bound of A. Or we can say there is no element which is above than A and related to A. If there does not exist any element which is upper bound of A except itself. If in a poset we are able to find some element which do not have any upper bound except itself, then such element we called as a maximal element. In the same way, minimal element is an element which do not have any lower bound, which do not have any lower bound if in a Hasse diagram or if in a relation there is an element which do not have any lower bound, which do not have any lower bound, we call it as minimal element. There is no other element which is related to A and lying lower than A. Then we call it as minimal element. Maximal element, no upper bound except itself. Minimal element, no lower bound except itself. In the same manner, we are having two more definition. One is called as a least element. An element is called as a least element if it is the lower bound of every element. Lower bound of every element. An element is called as a least element if it is the lower bound of every element. Lower bound means A comma B belongs to A is the lower bound. In the same manner, greatest element is an element which do not have, or better to say, a greatest element is an element which is the upper bound of every element. What we mean by greatest element? An element which is upper bound of every element. Least element, an element which is lower bound of every element. An element which is connected to every element on lower side. An element which is connected to every element on upper side. It's not necessarily direct edge should be there. When we are moving, we are able to reach on that spot. Okay, so this is how we can define the greatest or least element. So we talked about four things. Maximal element, which do not have any upper bound. Minimal, which do not have any lower bound. Greatest, which is the upper bound of every element, which is related to every element on upper side. Least element, which is the lower bound of every element. Okay, so one another important point is what when least and greatest element in a poset exist, they always unique if exist. It may a poset do not have greatest element. It may a poset do not have a least element. But if exist, they are unique. It is not true for maximal and minimal element. A poset may have more than one maximal, more than one minimal element. Okay. Now moving ahead, least upper bound and greatest lower bound. The least upper bound out of all the upper bounds of a set is called as a least upper bound of the set or supremum of the set. Now, the previous four definition is talking about individual. Maximal element. A is maximal or not. B is maximal or not. A is greatest or not. B is greatest or not. But when I'm talking about least upper bound, so it is, yeah, we can calculate it for the single element, but most of the time we are talking about for the set. We are talking about for the set. For example, least upper bound of A and B. What it means? It means we are supposed to write all the upper bound of A and B, the common upper bounds of A and B, and out of all those common upper bounds, we are supposed to choose the least one. All upper bound, upper side connected. Okay, all the common upper bound of A and B, upper bound connected elements, and out of those, the one which is the least one is called as the least upper bound or supremum of the set. Set means, in this case, I am talking about A comma B. In this case, I am talking about A comma B. In the same manner, the greatest lower bound of a set is what? The greatest lower bound of a set is what? Greatest out of all the lower bounds of that element. Greatest lower bound, also known as GLB. So GLB of A comma B means what? Firstly, list all the lower bound of AB, the common lower bound of AB, and out of those, whichever is the greatest one, we call it as the greatest lower bound or infimum of the set if it is A comma B. Greatest upper bound is the greatest lower bound means, as the name indicated, from all the lower bound, the greatest one. Least upper bound, from all the upper bound, the least one. What is the great? So if I'm talking about same element, least upper bound, to the common upper bound of A and A, the common upper bound of A and A, and we are supposed to write the least one, which comes as it is. In the same manner, if I'm talking about greatest lower bound of same element, that also comes as same thing. That means if I am finding supremum infimum, or we can say least upper bound or greatest lower bound of the single element, it comes out as it is. It comes out as it is. So total 6 to 7 definition we talked about. Let me repeat it quickly. The first one is the comparable element. If A and B are related to each other, we call them as a comparable element. If A is related to B, that means if A comma B belongs to R, A is called as the lower bound, B is called as the upper bound. Maximal element is an element which do not have any upper bound. Which do not have any upper bound. Minimal element is an element which do not have any lower bound. Least upper bound means what? Just write common upper bound, and out of those, the least one is called as the least upper bound or supremum. The same manner, the greatest lower bound or infimum means what? Out of all common lower bound, the greatest one is called as the greatest lower bound of A comma B. This infimum supremum all will play an important role when we are going to decide the given poset is a lattice or not. Okay, let us take some examples. So these are some of the hash diagrams we do have, and now we are interested to check or to find the maximal element, minimal, greatest, least for these hash diagrams. So for the first diagram, what is the maximal element? F is the maximal element because it do not have any upper bound. No element above than this and related to this. This is the maximal element. Minimal element, yes, A is the minimal element. Maximal, minimal. Okay. Now the next one is we discuss about the greatest element. Greatest element is the element related to every element. Upper bound of every element. F is the upper bound of E. Yes, it is connected. F is the upper bound of C. Yes, from C we can move to F. F is the upper bound of D. Yes, from D we can move to F. F is the upper bound of B. Yes, we can move. F is the upper bound of A. Yes, we can move it. So means we are moving following a particular direction. It's not like moving firstly up, then coming down. It is not allowed. Okay. So left, right is okay, but direction change is not allowed. So in the first part, maximal element is F, minimal element is A, greatest element greatest element is F, and least element is A. A is the lower bound of every element. From anywhere we can come down to A, B to A, D to A, C to A, F to A. From anywhere we can come down to A. So A is the lower bound, or we can say A is connected to every element on lower side. Talking about the second example, what is the maximal element? D, yes, no upper bound. E, yes, no upper bound. F, yes. So this is having three maximal element, which is D, E, F. because all the three do not have any upper bound. What will be the minimal element? The element which do not have any lower bound. So B do not have any lower bound, A do not have any lower bound, C do not have any lower bound. So A, B, C. These are the minimal element of this relation, or better to say the Hasse diagram. Now talking about the greatest element. Now talking about the greatest element. So what is greatest element? Which is upper bound of every element. Can I say D is the greatest element? The answer is no. Because D is not the upper bound of E. From E, we can't move to D. Like if I'm taking this, I need to switch the direction, which is not allowed. So D is not the upper bound of E. So D can't be maximal. Can I say E? No. E is not the upper bound of D. Can I say F? No. F is not the upper bound of E as well as D. So maximal element, I can say not exist. In the same manner, minimal element also not exist. There is no element which is lower bound of every element. There is no element which is lower bound of every element. Like if I'm talking B, so I can't move from A to B without changing the direction. So B is not a lower bound of A, so not a least element. An element which is the lower bound of every element. As in the previous example, A is the lower bound of every element. So in this example, neither least element exists nor greatest element exists, but maximal and minimal exist, and they are more in number, not one, they are three in numbers. Talking about the third example, what is the maximal element? I hope now you can understand it. E is the maximal element, no upper bound. D is the maximal element, no upper bound. Minimal element, A is the minimal element, no lower bound of A. Greatest element does not exist because D, if I am thinking for E is not the upper bound of D. If I am thinking on D, D is the upper bound of every element, B, C, A. But D is not the upper bound of E. So it is not a greatest element. Greatest element is an element which is the upper bound of every element. What about the least element? Yes, least element is A. For this Hasse diagram, the least element is A. A is the lower bound of B, yes. Lower bound of C, yes. Lower bound of D, yes. Lower bound of E, yes. From anywhere I can come down to A without switching the direction. So yes, this is the least element. So for the third figure, maximal is E and D, minimal is A, least is A, greatest does not exist. For the example number 4, maximal is this ABC, upper bound of every element. We can arrive to ABC from any point. We can arrive ABC from any point. So ABC is the greatest element, upper bound of every element, and it is also the maximal one because there is no upper bound of ABC. Maximal is which do not have any upper bound. Greatest, which is the upper bound of everyone. So in this example, maximal is ABC and greatest is also the same thing. Phi is the minimal element as well as the least element. Phi do not have any lower bound except itself. So phi is the least element. Phi is the minimal element. Also, phi is the lower bound of every element. From anywhere, I can move down to phi. From anywhere, I can move down to phi. So phi is the least element. So this is how we can understand these some important terminology related to a Hasse diagram. I hope you understand it. Now let us close the session. In the next session, we'll talk about the concept of lattice.